Hello and welcome to a problem-solving video on ratios, proportions, and dimensional analysis. This is the second video in problem solving. So the idea of a proportion is that you have two ratios that are set equal to each other, like A over X is equal to B over C. You can solve a proportion if X is the unknown. Then you cross multiply the A and the C and you divide by B. Now this comes from the idea that a proportion is when you multiply diagonally AC, it should equal to be equal to BX. You cross multiply, but then you'll divide both sides by B. And so that gives us this solution that X is equal to A times C over B. So here if X is unknown, if you multiply 3.5 times 5.2 and then divide by the 8, which is opposite of the X, that should give you what X is. It's just a quick calculation on your calculator. So to apply that, you have to make sure you're being careful and making sure that the proportion is aligned appropriately. So if you have something like dollars to gallons in one ratio, if it's equivalent, which is what a proportion says, that the two ratios are equal, then dollars over gallons should be equal to dollars per gallon here. So, and this is what we call the corresponding units should be aligned. So it may not be dollars and gallons, it might be whatever, might be feet and inches, and then it would be feet and inches if you're having an equation out of it. Now, when we do dimensional analysis, that's different than a proportion. So we won't align those on dimensional analysis. We'll actually have like units diagonal to one another. So it's a real distinction you want to pay attention to in these types of problems, knowing the difference between a proportion and when you're using ratios in dimensional analysis. And we'll get to that. So when you're walking on a treadmill, the readout indicates that after 10 minutes of brisk walking, you have burned 60 calories. At that rate, approximately how long would it take you to burn 800 calories through brisk walking? So that, notice it says at that rate. So that means we're going to have the same rate. So that means every 10 minutes, and I'll write it this way, this is a ratio, every 10 minutes burns 60 calories, which means, of course, after 20 minutes, you would burn twice as many, or 120 calories. After 30, you'd burn 3 times as many. So the question is, how many minutes would you have to walk briskly in order to burn 800 calories? So that should be a proportion. And so you should have minutes in the numerator, as here, and calories in the denominator. And notice we want to burn 800 calories, so the 800 goes with the calories. And the minutes are what's unknown, and so we will cross multiply and then divide. So here's our unknown. We'll cross multiply the 10 minutes, and I'm going to write the units this time. 10 minutes times 800 calories divided by 60 calories. And now the units, since the units can reduce, just like numerical factors, the units reduce here, and you can see we're left with minutes, which is appropriate because we're trying to find how many minutes it will take to burn that many calories. And so now we can go ahead and do this division, or you can go 10 times 800 over 60, but you could reduce the 10 and the 60, dividing them both by 10 before, since this is a multiplication and those are factors. So if they're all multiplication, you can reduce before you actually multiply. Now you couldn't do that if that was addition or subtraction, but only on multiplication. So we get 1 times 800, which is 800 over 6, and that's going to be minutes. Those are the only units left. And so we'll divide 6 into 800. You can do that on your calculator really quick. And that's going to be 133, and it says 0.3 repeating minutes. Well, this is just walking on a treadmill, and the truth is it says at that rate, which means it would be the exact same rate. It would take you exactly that long if it were really the exact same rate. We know that a machine doesn't actually tell us exactly how many calories are burned. That's impossible for it to do, really. consistency. Machines can't evaluate that. So this 133.3 minutes, you'd probably round it off to maybe 130 minutes if you wanted. Or you could say, since 2 hours, an hour is 60 minutes, 2 hours 120 minutes, you could say that's 2 hours and 10 minutes, or 13 minutes if you wanted. Or you could say 13.3 repeating if you wanted to be real precise. 2 hours and 13.3 repeating minutes, since it did say it's at the same rate. Okay, so that's the basic idea of proportions. Now, I got to say this, these units should work out every time, as you can see, if you have them corresponding units aligned properly. But you could have set this up differently. You could have said, well, what if I want to look at, if I set up the ratio 60 calories takes 10 minutes to burn, and then 800 calories will take X minutes to burn, and still X is here, so the 800 and the 10 we'd cross multiply, you'd still get X is equal to 10 times the 800, and we divide by the 60. Well, those are the same numbers we got over here. Notice I'm not going to keep the units, so this will be the, I don't have to use the units if I have them aligned properly to begin with. It's obvious they're going to work out to be X minutes. So this will give you the same exact result, even if you set it up, if you invert both of those. But again, notice it's calories to minute and calories to minute. So you have the units aligned in a proportion. And remember, this says it's equal to. So units have to align if it's equal. Okay. So let's take a look at this. Wild Horse Wind and Solar Facility, and that, by the way, is just up in Ellensburg, has the capacity to produce 273 megawatts, which is enough to provide power for 63,000 homes in central Washington. So just so you get an idea of what a megawatt is, a mega, it means a million. So a microwave oven usually requires energy coming in at about 1,000 watts or a kilowatt. And a megawatt is 1,000 kilowatts. So 1 megawatt will run 1,000 microwave ovens. So just so you get an idea, that's 273,000 microwave ovens that these could run. Anyway, it's enough to power about 63,000 homes, various in central Washington. Now, in which that changes, because if someone's not running their microwave, they don't need as much energy, or if their air conditioning isn't running, or their dryer, or the heater, so whatever electricity you're using. So this number, how much each home is using, varies quite a bit, depending on what they're doing in that home at the time. So about how much power would it take for nearly 3 million homes in the state of Washington if the power needed was similar throughout the state? Which we know it's really not. Central Washington has a high demand for power because of the extreme temperatures of cold and heat that we don't get, and most of the people in the state don't have that over on the west side. Anyway, there's 3 million homes for about 7 million people, a little over 2 people per home. So notice the proportion, the ratio, 273 megawatts for 63,000 homes, and they want to know how many megawatts to do 3 million homes. So I'm going to write that first. The proportion that we have is 273 megawatts will provide power for 63,000 homes. And so to use a proportion for this, we have to say how many megawatts, right? We've got to have megawatts up here to correspond and homes down here to correspond because it's equal. And this was going to be 3 million homes. Well, that's 3 with 6 zeros. I'll have to squeeze those in. 3 million homes. So here's our unknown. We're going to cross multiply what we do know and divide by the 63, whatever's opposite the variable. So that should be X should be equal to 273 times 3 million. 6 zeros there. Over 63,000. And we know the answer is going to come out in megawatts, right? You'd have This would be homes, this would be homes. The homes would reduce out with megawatts. But notice that we can reduce some of those zeros too. I can divide this by 1,000 and this by 1,000, again because it's multiplication, not adding or subtracting. And so now I get 273. I'm going to do that on my calculator. So my calculator gives me 13,000, and that was right, megawatts, right? And this tells us a little information. It says use gigawatts using the fact that 1,000 megawatts is 1 gigawatt. So I'm going to have to do a conversion, which we haven't done any of those yet. So how do we change 13,000 megawatts to get gigawatts? Well, this is not, we could use a proportion here, but we could use a unit ratio. To go from megawatts to gigawatts, we could put megawatts in the denominator. See, notice we're going to multiply these. We're not saying this is not going to be this is not a proportion. We're going to multiply 13,000 megawatts and convert it to gigawatts. So the megawatts will reduce. But it is 1,000 megawatts is 1 gigawatt. We're going to use that fact. And so what do? We're going to get 13,000 times 1 over 1 times 1,000, which is 13,000 over 1,000 will reduce, and that will just give us 13 gigawatts. Okay, let's move on to the next problem. So now if a 7,500 watt solar array costs $28,500 to have installed, how much will it cost to have an 8.5 kilowatt solar array installed, assuming a consistent rate per watt for installation of materials? So if we set up a proportion, we already know that 7,500 watts costs $28,500. So now we're going to have how many, right? We got to have these units the same, watts compared to watts, and then dollars to dollars. So how many watts are we looking at? Well, this says 8.5 kilowatts. Well, since that's kilowatts, and this says watts to dollars, that kilowatt, we can't put 8.5 in there because these have to be the same units. So we have to take that 8.5 kilowatts and convert it so it's watts. So I'm going to use this unit ratio multiplier. The unit ratio, the kilowatts, to get rid of kilowatts, we multiply by a ratio that relates kilowatts to watts. And it says 1 kilowatt is 1,000 watts. So we put those appropriate values, numerical values in there. And there's no reducing on this one other than the units, kilowatts. 8.5 times 1,000. Well, you know that when you multiply by 1,000, that should move the decimal point 3 places to the right. So the 5 is 1 place, and that should give us 2 more zeros. So that should be 8,500 watts. Now we can set up the problem, okay, in our proportion. So you have to come over here and do a little conversion before we can set this up, and this is X dollars. So now our unknown X, to solve that, we cross multiply the two numerical values that are opposite each other, and then divide by the whatever's opposite of the X. So just a reminder, that's because on the means and extremes theorem, you would multiply diagonals, and you'd multiply those diagonals, and then to solve, you divide by 7,500. I usually don't write out this part here. I just cross multiply and divide. And so again, notice you're going to be able to do some reducing here. You could divide by 100 and reduce out 2 zeros on each of those. You can do more reducing, but since we get a calculator, we'll just use the calculator. So I get 32,300. Now that should be dollars, right? Because this was really dollars, this was watts, and this was watts, so the watts would reduce and we'll get dollars. So that's what it would cost if it was proportional. That means if the rate per watt was consistent. Okay, so next, two blocks of the same type of cheese are being offered for sale. The blocks are cylindrical with the same height, but one has a 3-inch radius and the other has a 4-inch radius. So I'm just going to kind of draw those. I don't know what the height is. It doesn't matter because it said they're the same height. As long as those are the same. And it could be a lot deeper. If you wanted to draw them bigger, that's fine. But it said those are the same. So that's not going to make that won't make any difference in how much is in it. So this is it said a 3-inch radius and a 4-inch radius, which is really, that's a 6-inch diameter, right? And that's an 8-inch diameter. But they gave us those radius. Now, I would compare their volumes, but it tells us that their heights are the same. So the smaller one is priced at $14.99. So you can't just go. It would be a mistake to take $14.99 and compare it to 3 inches and then have a dollar assigned to 4 inches because the whole area changed. The area of the cheese, which affects the volume, is pi times the radius squared. And this is pi times this radius squared. Now, they both would have a height, which we don't know. That would be the volume. We don't know the height, but that means we'd have, it's $14.99, not for 3 inches, but for pi r squared. I'm going to call that 9 times the height, that volume. And this would be this would be pi times 16 times the height. And usually in math, we try to avoid multiplying by pi unless we're kind of at the end of the problem, because it's just a lot easier to keep it as pi all the way through. So this will be equal, and this is the dollar sign. We do not know what this is, right? That's our x dollars. So we're going to cross multiply and divide. So we'll get x is equal to $14.99 times pi times 16h over pi times 9h. And notice what happens. Since the heights are the same, those will reduce out. Pi is the same. That'll reduce out. And we're just left with $14.99 times 16 over 9. So 14.99 times 16 divided by 9 is $26.65 approximately. I mean, it gave me 6,488 repeating. That is quite a bit different than just going 3 to 4. Had you done it that way, you wouldn't be taking into account the much larger volume when the radius increases. So it's based on 3 squared, which is 9, and 4 squared, which is 16. Okay? All right, let's jump ahead and do some dimensional analysis with converting. We've already kind of set this up, but these are going to be a little more interesting than the trivial ones we did with kilowatts and watts. Those are pretty easy in the metric system, but you probably want to write down some of those things for the quiz, because you don't want to be looking that up in the middle of a quiz. So you're going to want to keep the units for metric units, write those down so you've got those. Now, this says convert 210 centimeters to feet. So I'm going to write that as 210 centimeters. Now, there is a way of doing with a proportion. You can change 210 centimeters to inches, and then you change inches to feet using proportions. That means equations. But we're going to use dimensional analysis. And dimensional analysis is also lends itself to a process of problem solving that is very, very handy. So you're going to be seeing a lot of dimensional analysis if you haven't seen that before. So how do we convert centimeters to feet? Well, think of it as kind of a trip. You've got to map it out. If you're going from Yakima to, let's say, Zilla, you really have to go through Buena on the way, right? You drive right through Buena. You actually go through Parker too a little bit there if you're on Highway 84 there. But 210 centimeters, we're going to have to go from centimeters to inches first, and then from inches to feet. So it's like to get from centimeters to feet, we got to go through inches here. So we're going to change, here's what you do, centimeters are here. So in order to eliminate centimeters, if centimeters is in the numerator, we'll put it in the denominator, and the new unit we'll put in the numerator, and then we'll put the numerical values in after. I always add the units first, because the units give us the directions, not the numbers. So make sure you put your units in first, and then make sure you have the appropriate numerical value corresponding to each unit. Now, if you want, you can take this 210 and put it over 1, because it's not a fraction, we're going to multiply by a fraction. Now that takes centimeters and converts it to inches, so these centimeters will reduce. And now in the next unit ratio, how do we get from inches to feet? If inches is in the numerator here, we're going to put inches in the denominator here, so it will reduce just like centimeters did. And inches will go to feet this way. And so there's 12 inches in 1 foot. And now our inches will reduce, and the remaining unit is feet, which is what we wanted in the first place. So now what do? We get 210 times 1 times 1, which is 210. And we get 1 times 2.54 times 12. So we might want to go 2.54 times 12 to get that denominator of 30.48. And then I'm going to take 210 and divide it by, actually I usually go second answer because that tells me what, 30.48. And I get 6.889, and it goes on and on and on, feet. So I'll say about 6.9 feet approximately. Okay, so it's that simple. Now that's pretty good old-fashioned simple dimensional analysis for a conversion. Now let's take and convert a rate. Now rates are different. When you invert a rate, notice it has the word per in it. Feet per second, which is abbreviated FPS. And we're changing that to miles per hour, mph. Now feet per second should be written like this. 88 feet per second, we should write like this. Feet per second is feet over, this is over 1 second, okay? 88 feet is a long way to go in 1 second, isn't it? It's quite a long way to go. So we're going to change it to miles per hour. So now notice that I like to write the end too. Where do we want to end up with? We want to end up with miles per hour. So over here in the end, we're going to have miles in the numerator over hours in the denominator. And we really want this to be 1 in the end. We might have to divide to do that. So in order to do that conversion, we're going to have to take feet. Our feet unit, our distance unit, corresponds with that distance unit, right? Here's feet is a distance and miles is a distance. Seconds and hours correspond. Seconds is a time unit and hours is a time unit. So we're going to get rid of feet and get miles. Now, you can look this up if you need to. You put feet in the denominator, because remember, this is not a proportion now. This is a dimensional analysis, so we're multiplying by a unit ratio. So we want our feet to be able to get reduced, and we want miles to be introduced, the new final unit. So 1 mile, you may need to look that up, is 5,280 feet. And that will mean we get rid of the feet and get miles. So notice now that I have miles is all taken care of. The numerator is fine. What's the problem? The denominator is not. I have to convert seconds to hours. So now, at the same time, I can get another unit, and I want to get rid of seconds. But now seconds is in the denominator. So where am I going to put that in my new unit ratio? Well, in order for that to reduce from the denominator, seconds will have to be in the numerator in this unit ratio. And I know that now some people know how many seconds there are in an hour. If you know that, that's great. You can go seconds to hours. But it's kind of like, going from Yakima to Zilla, we got to stop in Buena on the way. So seconds would go to minutes. That's part way through. And we know there's 60 seconds is 1 minute. And then we have to get rid of minutes. So notice doing this, our seconds will reduce out, but now we have minutes in the denominator, not hours. So we have to get rid of minutes. So again, if minutes is in the denominator here, in order to reduce those units out, we need minutes in the numerator here, and that'll go to hours. So 60 minutes is 1 hour. At this point, some of you may notice, and of course the minutes drop out, that 60 seconds and 60 minutes, that's 3,600 seconds would make 1 hour. So we know that there's 60 seconds equals 1 minute, and 60 minutes equals 1 hour. If you have to do seconds to hours ever again, you can just use 3,600 seconds is equal to 1 hour, and that's a little shorter. It's kind of like flying. You don't have to stop and go through beyond it. Go over it. So anyway, now we could do some multiplication here. Look at all these numerators we could multiply, and then the denominators we'd multiply. And by the way, let's emphasize something here. Notice that the only unit left unreduced in that dimensional analysis is miles in the numerator and hours in the denominator, which is what we needed. Okay? So we get 88 times 60 times 60, or you could really quickly divide by 10 so you could knock off one of those zeros. Then we get 88 times 6 times 60 in the numerator, which is 31,680. And then 1 times 528, well, we could have just divided that straight, divided by 528. And that turns out to be what? 60 miles per hour. So 60 miles per hour is 88 feet. 88 feet per second is the same as 60 miles per hour. So that is very fast. I mean, relative to, someone isn't running or riding a bike that fast. Okay, next let's convert 25,000 psi to tons per square foot. Now, this is something you're not maybe as familiar with. This is pressure. That's supposed to be 25,000 psi. So if we take 25,000, now psi stands for pounds per square inch. So this would be pounds here per divided by 1 square inch. Now, we've got to change pounds, has to change. Notice this is what we're going to go to. We want tons over square feet. So, one thing we're going to have to do is change pounds to tons. You may need to look that up. How many pounds are in a ton? And again, emphasize that if pounds is in the numerator, we did it in the denominator. So it'll reduce out. And it says 1 ton will be the same as 2,000 pounds. And of course, you can look that up. You can Google it in a heartbeat. You can get that. And then, and then of course, our pounds will reduce. If you want to, you can reduce by divide both of those by 1,000 too. You can reduce the numbers as we go along. But before we're done here, before we stop, remember we've got square inches and we want to go to square feet. Now this is something that throws a lot of people off. Square inches, a square inch is not the same as an inch. And a square foot is not the same as a foot. So we know that 1 foot is equal to 12 inches, right? So, but a square foot is something that's 1 foot by 1 foot square. Okay? Well, something that's 1 foot by 1 foot is also 12 inches by 12 inches. And the area, and by the way, this square unit, that's an area unit. You're comparing areas. So when we use a unit ratio here, these are called unit ratios. When you use this unit ratio, you're going to have to change square inches. So you can't just put inches, you have to put square inches there. And that will have to convert to square feet. And so 1 square inch is a little tiny thing in here. There'd be 12 of them all along here. And there would be 12 of them, 12 rows of them all along here, right? 12 by 12. It would be 12 by 12 which is 12 squared, is 144 square inches is 1 square foot. So 1 square foot is equal to 144 square inches. And I'll use that little 2 up there. That's usually how we abbreviate square feet with a little second power. And so now our square inches will reduce. And look at what we'll get in the denominator. 1 times 2 times 1. And then the numerator is 25 times 144 times, of course, 1. So I'll just do that all at once. 24 times 140, oh, sorry, 25. 25 times 144, and divide that by 2. And that's going to give me, I'm going to rewrite this. That's going to give me 1,800, and that is tons slash per square foot. 1,800 tons per square foot. Okay? So that's converting with just, simple units, centimeters to feet, but also you have rates, and those are more interesting conversions. Okay, now let's use this as in an application. What would the average speed be in miles per hour for a person who can run 100 yards in 10 seconds? So notice we want miles per hour. This is a distance, and this is a time. So we want distance per unit time. We want our answer, we want miles over hours. So in the beginning, if we got miles here, we're going to want a distance. This is a distance over a time. So we're going to want to start out with a distance over time. So that's 100 yards in 10 seconds. So that's a distance and a time. And so what do we need to do? We're going to convert yards to miles. Those are 2 distances. And seconds to hours. Those are 2 times. And so what do we get? We want to get rid of yards and get miles. So you might need to Google that. 1 mile is 1,760 yards. And that will reduce yards. And then, you could probably reduce one of those. You could reduce one of those zeros there, and you could reduce one of those zeros there if you wanted. So not much to do yet. But now we also have to get rid of seconds and change those to hours. Well, you may remember just a couple minutes ago, we said, hey, if you get across this, if you remember that 3,600 seconds is 1 hour, you can just write 1 unit ratio, and you don't have to write the 60 seconds per minute and 60 minutes to an hour. So this is all we'd have to do. Now we get 1 times 3,600 over 1 times 176 times 1. And by the way, I didn't do this, but I should be crossing out those seconds and seconds, right? And notice we just have miles in the numerator and hours in the denominator remaining. And so 3,600 divided by 176 is 20.45 repeating. Now this is a person who's running 100 yards in 10 seconds, and that could be a very precise time, but 20.45, you could leave it as 20.45. You could round it off to say it's about 20.5 miles per hour if you wanted. Okay? So anyway, there we go. Next. Okay. I'm going to pause this video, and we're going to come back and do a second. And in the second one, I'll do problem 7 and 8 and 9.